All right, time to get started. Does anybody have any questions from homework or anything like that before we get started? All right, sounds like we're doing okay. Well, today we're getting into chapter 4 a bit more, graphing polynomials, looking at how to understand the graph a bit better. Last week we introduced the idea of end behavior by looking at the lead coefficient, or the leading term, and so we'll carry that on a bit more. If I had a function that was f of x equals negative 2x to the fourth plus 3x cubed, and we're asked to graph this, maybe we'll take a coordinate system here. Well, we can start with the end behavior. Because we've got an even degree, both ends of the graph are going to go the same direction, either both up or both down. Because it's a negative, we know that it is both down. So it's going to be down here and down here somewhere. Not sure where. It'd be awful nice if we knew where this crossed axes. Well, where it crosses the y-axis, recall that's our y-intercept, and we get that by setting x equal to 0. So if we found f of 0, say negative 2 times 0 to the fourth, plus 3 times 0 cubed, well, that's 0. So our graph is going to cross the y-axis at the 0 value. So now we need to find x-intercepts, and we get x-intercepts by setting y equal to 0. So we set our function equal to 0, and we solve for x. Now, because each of these terms has x in it, I could potentially factor x out, and it looks like I can even factor x cubed out. I'm going to go ahead and factor negative x cubed, because I like my leading coefficient to be positive. So we get 2x minus 3, and that equals 0. So I can set each of these terms equal to 0, say negative x cubed equals 0, and 2x minus 3 equals 0. So over here, I would, dividing by negative 1, say x cubed equals 0. So x would be 0, and we already had that because of our y-intercept. Over here, add 3 to both sides. So x would be 3 halves. So that's our other 0. 3 halves is 1.5. That'd be right about there. Now we need to figure out what happens in between there. As a reminder, we also talked about multiplicity, and that's when your factor is raised to an exponent, like we have over here, this x cubed. And recall that an odd multiplicity passes through but has a little jog in it. So I expect this graph to come up and kind of jog through and go up. And then somewhere it's got to turn around and come back down, somehow back through here and head down. So the graph is going to look something like that. The important thing at this point is to get the zeros and get the proper end behavior, as well as the multiplicity, so you know what's happening at each 0, and then you can graph it about like that. Now, in the homework, they give you several graphs to pick from, and you pick the one that applies. So my recommendation when you have multiple choice like that is try to find a way to eliminate some of the options. So for example, we already knew, because of our leading term here, we knew the end behavior of the graph. So all of the options that had end behavior going up or one up and one down, we can eliminate those. None of those applied. And so you're down to just, you may eliminate all three of the other ones, or you may just eliminate two, in which case then you only have two to look at, and you can tell by the zeros then which one would be the correct one to pick. So that's just kind of some words to the wise there. So when you've got multiple choice, eliminate as many as you can, and then use the information we have, like the zeros, to pick the correct one out of the remaining options. I think you'll find that's a good way to handle this. Sometimes we've got one that looks a little worse, or a little more challenging, I should say. Something like f of x equals 2x cubed plus x squared minus 8x minus 4. Once again, we've got, looking at the leading term, we can tell the end behavior. We have an odd exponent, and the leading coefficient is positive, so it'll be up to the right, down to the left. Now, something I'd like to point out, the degree of the polynomial tells us how many zeros max, how many real zeros we might expect. So at most, we have 3 zeros because it's a third degree polynomial. That means we can expect 3 x-intercepts. And at most, we would expect, get the right term here, 2 turning points, or places that it changes direction. And that is always 1 fewer than the degree. So if I said this is nth degree, say it was a 5, this would be n, this would be n, and this would always be n minus 1. Just something to keep in mind. You do have some homework problems that will ask you the max number of real zeros, the max number of x-intercepts, and the maximum number of turning points, and those are based on this formula. That the degree of the function is the max number of real zeros, which is the max number of x-intercepts, and we subtract 1 from the degree to get the maximum number of turning points. So let me point something out here. The ratio of, oh, let me get a color. I changed color for a reason. I've got 4 terms here. So it's not a quadratic, it's a cubic. If the ratio of coefficients of the first and second term is the same as the ratio of the coefficients of the third and fourth, you'll want to consider factor by grouping when you have 4 terms like this. So I'm going to do that. Out of these first 2, I'll factor in x squared. I'm left with 2x plus 1. Out of this second binomial, I'm going to factor a negative 4, and that leaves me with 2x plus 1. And that's why you want those ratios of the coefficients to be the same, so that you end up with the exact same binomial inside here. Because now I can factor that binomial out, and I'm left with the numbers I factored out at first, x squared minus 4. Now these equal 0 because we're trying to find the zeros of the functions, so I can set each one of those factors equal to 0. So here I'll have x is a negative 1/2, and here we'll get x equals plus or minus 2. We would bring the 4 over and take the square root. So there I've got the zeros. I've got negative 1/2, which is right there. I've got positive 2, I've got negative 2. So those are my 3 zeros. Well, these are the 3 zeros. These are the 3 x-intercepts. And behavior of my graph, I had to come up one. And of course, I drew them way out here, and they actually, now that I know, have to be more like this. So I expect 2 turning points, and that makes sense. In order to get through here, it's got to go straight through. Notice the multiplicity of each of these is 1. So it's got to go straight through each time. So it's got to turn up here somewhere, and it's got to turn down here somewhere in order to get the right direction. And we can find those just by plugging values in. Let's plug in -1, find f of -1, and see just how high up the graph goes at -1. So 2 times -1 cubed plus -1 squared minus 8 times -1 minus 4. -1 cubed is -1 times 2 is -2. -1 squared is a positive 1. -8 times -1 is a positive 8. And subtract 4. So that looks like 9 minus 6, which is 3. So at -1, it's up here at 3. So looks like my graph comes up through there somewhere and heads down. Now we can plug in a positive 1 to see how deep it drops over there. F of positive 1 is 2 times 1 cubed plus 1 squared minus 8 times 1 minus 4. We've got 2 plus 1 minus 8 minus 4. 2 plus 1 is 3. Minus 8 is -5. Minus 4 is -9. So it actually drops all the way down here. So it's going to come all the way down to there and then go up through. So I feel like I made a mess of that graph. Let me change color. Maybe that'll help. So it's going to come straight down here, up somewhere through there, down to 9, and back up through. That's no better than I had before. So I'll just leave what I had. Let's see, not that one. There we go. All right, not a great graph maker today or yesterday, but that's how we can graph these. Again, I used my leading term test to find the end behavior of the graph. I know how many zeros because it matches the degree. Now that's a maximum, remember. If you've got a multiplicity of 2 somewhere in there, that's going to reduce the number of real zeros. Maximum number of x-intercepts matches the degree. Maximum turning points is the degree minus 1. And we had 2 turning points, so that fit. All right, do we have any questions on this so far? All right, I'd like to do one more before I jump into the next section. And this one, they actually give us the factors, which is nice because they're not super easy to find right now. X to the 4th minus 7x cubed plus 12x squared plus 4x minus 16. And they tell us that that factors into x plus 1. Now, by the end of the week, you'll be able to find all of these factors. Times x minus 2 quantity squared times x minus 4. So our leading term test tells us that the graph, because it's a 4th degree, An even degree, I expect both ends of the graph to go the same direction. Because it's positive, they'll both go up. So something like this. Looking at now our zeros, we're going to set this equation equal to 0, so each factor equals 0. So we'd get x equals -1, x equals 2, and x equals 4. So when I graph this now, I've got -1, I've got 2, and I've got 4. But notice this multiplicity on that 2. Multiplicity on this one is a 1, and on this one is 1. So I know the graph is going to go straight through at those points. But because the multiplicity is even on this one, I know it's going to, what I always call bounce, so it's going to hit and change directions. This works because it needs to come up here somehow. It needs to come up here somehow. It's going to change direction in the middle somewhere here. It's going to change the direction in the middle somewhere there. Now it turns out, let's think about this for a minute. If I find g of 0, get the y-intercept, I've got 0 to the 4th minus 7 times 0 cubed plus 12 times 0 squared plus 4 times 0 minus 16. And all of these terms are going to go to 0 because anything times 0 is 0. So g of 0 is -16. So this graph actually drops way down here and comes up, bounces, and I could find g of 3 to find how far it drops here, and I don't think it drops very far. We could test it. Clearly not a great graph, but if you gave me this on your test, if we were taking a paper test, and you wrote this down, you would get full credit because you've got the zeros, you've got the end behavior right. Yeah, my lines are crooked, but I know that you hit the main points. In my math lab, you will be given, like I said, multiple choice, choose the graph that fits. And so eliminate the ones that clearly don't using the leading term test, find the zeros, and then choose the graph that matches those zeros. I think you'll find that's the easiest way to do it in my math lab, which means the test will be similar because that's also in my math lab. It is this weekend, by the way. It'll be available to you Thursday morning through Sunday night, and it will cover chapters 3 and 4. All right. We've got another concept in this section, and before I leave that, I'll leave the graph here. Before I leave this section, I want to cover this. It's the intermediate value theorem. And the intermediate value theorem, I think, is one of the weirdest things to call a theorem. But what it says is if you have a graph with a y value above the x-axis and a y value below the x-axis at another point, there has to be somewhere between there where you have a 0. So if you've got a polynomial that comes here, the only way it can get down to this point is if it actually goes through the x-axis. So there has to be a real 0 between 2 points on a polynomial's graph that are on opposite sides of the x-axis. And that's why I think it's silly, because it's, to me, it's a no duh. How do I get from there to there without crossing that? But let me show you how we test this. If I have f of x equal to x cubed plus x squared minus 6x, and I need to know if there is a real zero between -4 and -2. So is there a real zero between there? Well, let's go ahead and test both of those. We'll find f of -4. So we've got -4 cubed plus -4 squared minus 6 times -4. And -4 cubed is a -64. -4 squared is a positive 16. -6 times -4 is a positive 24. So this looks like, let's see, the sum of those two would be 40. And -64 plus 40 is a -24. That's one of the things I do in my head is I look for things that I can add quickly to simplify the work. Now let's try f of -2. So we've got -2 cubed plus -2 squared. And you have problems like this in the homework where they ask you if there's a real zero. Just quick evaluate the function at these zeros and see if they're different signs. -2 cubed is a -8. -2 squared is 4. -6 times -2 is a positive 12. 12 and 4 are 16, minus 8 is a positive 8. So because this is positive and this is negative, the only way I can get from one to the other is if there is a real zero. So the answer is yes. And I think it really is just a yes or no question in the homework. If I recall, that was what I saw. So just evaluate the function at each of those. If you've got a sign difference, the answer is yes, there is a real zero between them. Again, different ways to view these polynomials, their graphs, and how to differentiate between them. So now we need to figure out how to find zeros when it's not a polynomial that's easy to discover. And that's in section 4.3. So before I go to that, are there any questions on 4.2? All right. And I'll go ahead and jump into 4.3. What we need to do now is a little bit of division. So the first thing I'm going to do is just old school long division and show you that you remember what we're talking about. So if I've got 3642 and I'm dividing it by, I don't know, let's say 6. No, that's not a good one because that'll go in evenly. Maybe 7. Okay, so what we would do is we would look, how many times does 7 go into 3? It doesn't, and some teachers would tell you to put a little x above that to keep your place. And then we would look at the first 2 digits. How many times does 7 go into 36? And the answer is 5, because 5 times 7 is 35. So we first divided 7 into 36, gave us our whole number. We're ignoring the remainder right now. And then you multiply 5 by 7. And then we would subtract. 36 minus 35 is 1. We would bring down the 4. How many times does 7 go into 14? It goes twice. 2 times 7 is 14. We would subtract that, get a value, bring down the next number. How many times does 7 go into 2? It doesn't. 0 times 7 is 0. We would subtract that. We would get 2. Because we're at the end of our number, that's our remainder down here. So we might do remainder 2. And so we could say that 3642 divided by 7 equals 520, remainder 2. Or we could say that 3642 equals 7 times 520 plus 2. So you've got your divisor times your quotient plus the remainder. Now they're going to ask you to put things in this format. That's why I took the time to write that down. So let me get the right. They'll say that f of x, now this is polynomial division we're dealing with, is equal to x minus c, which is our factor here, times the quotient, which is some function of x, plus the remainder. That's the way they're going to write this. And so now I'll show you what polynomial division looks like, and you'll see that it's incredibly similar to what we just did. So let me get a polynomial here. We are going to divide x cubed plus 2x squared minus 5x minus 6. We're going to divide that by x plus 1. And then we're going to divide it by x minus 3. So I'll do both of these here. If this really, what we're dividing it by, is a factor, if x minus 3 is a factor of this polynomial, then our remainder is 0. Anytime you divide this out and get a remainder of 0, then that means you found a factor, which makes sense. All factors go in evenly, right? So let's go ahead and take a look at this and see if we get a remainder of 0. Now the difference here is that I'm going to ask, what do I multiply this by to get that? And I'm really only going to look at the first term in this binomial. So what do I multiply x by to get x cubed? And that's x squared. And now I go ahead and multiply the x squared through. X squared times x is x cubed. X squared times 1 is x squared. And now I need to subtract this binomial. X cubed minus x cubed is 0, so I'll just leave that. 2x squared minus x squared is 1x squared. Now I bring down the next term. And what do I do to x to end up with x squared? I multiply it by x, right? So I'm going to go ahead and add x up here. X times x is x squared. X times 1 is x. I subtract those. I'm going to change color here a little bit. X squared minus x squared is 0, so I'll leave that. Negative 5x minus x is negative 6x. Now I bring down that last term. What do I multiply x by to get negative 6x? Well, that's negative 6. Now I multiply that through. Negative 6 times x is negative 6x. And negative 6 times 1 is negative 6. And I subtract this whole thing. Negative 6x minus negative 6x is 0. Negative 6 minus negative 6 is 0. So because we ended up with a 0 remainder, this binomial that we divided by is a factor, and this is our quotient. So there's our quotient. Here's our remainder. This is our dividend, which they write as also x minus c. And they do that because c is the 0. So this is like x minus negative 1. So negative 1 is a 0 of f of x. X plus 1 is a factor of f of x. So that's the difference between a factor and a 0. The factor is the binomial. When you set that equal to 0 and solve for x, you get the 0. And we know that because our remainder was 0. That's what showed that. Now let's go ahead and do this over here with x minus 3. What do I do to x, or what do I multiply x by to get x cubed? That's x squared. And I always write it above the one with the matching degree. It just keeps things organized and I know when I'm at the end. X squared times x is x cubed. X squared times negative 3 is negative 3x squared. Now I need to subtract that. Now, if it helps you, go ahead, remember subtraction is adding a negative. Go ahead and add and change the signs of the things there, and now you're adding. That's the same as dividing, or subtracting, I'm sorry. Subtraction is the same as adding a negative. So if you make it a plus and change the sign of both, sometimes that helps. X cubed plus negative x cubed is 0. 2x squared plus 3x squared is 5x squared. Bring down the negative 5x. What do I multiply x by to get 5x squared? Well, that's 5x. 5x times x is 5x squared. 5x times negative 3 is negative 15x. Need to subtract that. I'm going to go ahead and add a negative, so I'm changing the signs and going to add. 5x squared plus negative 5x squared is 0. Negative 5x plus 15x is 10x. Bring down the negative 6. What do I multiply x by to get 10x? Well, that's 10. And notice this last one will always be a constant, won't have an x in it. 10 times x is 10x. 10 times negative 3 is negative 30. I need to subtract that. Again, I'm going to change it to adding a negative. 10x plus negative 10x is 0. Negative 6 plus 30 is 24. So I have a remainder. X minus 3 is not a factor, which means 3 is not a 0. So now we've proven that x minus 3 is not a factor and so on. But I want to show you something. Let's do f of 3. So we're going to plug 3 in for x in this polynomial. So I've got 3 cubed plus 2 times 3 squared minus 5 times 3 minus 6. 3 cubed is 27. 3 squared is 9 times 2 is 18. Minus 5 times 3, which is 15, minus 6. So I've got 45 minus 21. Well, that's 24. Look at that. F of 3 is the remainder you get when you divide by negative 3. And it will always be that way. Always. So if I did f of negative 1 up here, I would get 0. We did f of 3 and we got 24. We got that remainder. It's always going to work that way. So sometimes it's nice to do the division instead of plugging in the number into the polynomial like this. Now, I'm sure you're doubting that because we used long division here. I'm going to show you a shorter way here in a minute called synthetic division. It's pretty fast. And so just know that if you do the division, it's the same thing as evaluating the function for that 0, this value we subtracted from x. So that's good to know. Before I move to synthetic division, though, I do want to point out that notice the degree of our quotient always one less than the degree of the function. And that's going to be key, because I started with an x cubed. Let's look over at the left-hand side where I actually found a 0. Well, now my quotient is a quadratic. I can plug that into the quadratic formula and get the other two zeros directly. I don't have to guess and try to find a new one. I can, once I'm down to a quadratic, plug that straight into the quadratic formula. That's going to save you a lot of time later on. I guarantee it. Once you get a quotient that's a quadratic, plug that into the quadratic formula to get the other zeros. Do I have any questions before I go to synthetic division? Hoping I can make this as easy as possible for you. All right, let's do this same function, but with synthetic division. We should get the exact same numbers. So what I'm going to do is I'm going to keep this up here, and I am going to try to block out everything below that. If I do this right, I'll have some space where I can write, and you'll see that we'll get the same result. And I want to write the remainder up here as a reminder. This was a remainder of 24, and this was a remainder of 0. Okay, so with synthetic division, first what they did was they looked at the long division and they said, you know what, we rewrote x a lot of times. More times than we really needed to, perhaps. So what if we eliminated all that rewriting of the variable and just worried about the numbers? Because it's really the numbers that mattered. So if we take a look at this function, and I just use the numbers, I've got a 1 for the x cubed, I've got a 2 for the x squared, I've got negative 5 with the x, and then I've got negative 6 as a constant. Now I'm going to divide down. This organization works a whole lot better, and what I'm going to divide by is not the factor, but the corresponding 0. Remember I said negative 1 was a 0 over here. Where the factor is x plus 1. The 0 is what you get when you set that equal to 0 and solve for x. Now this is a process. And once you get this process down, it works really well. First thing you do is drop that leading coefficient straight down. And now we're going to multiply negative 1 times 1 and write it up here. I'm going to go ahead and write that in, though I almost never do. Negative 1 times 1 is negative 1. And now what I do is I just add these. 2 plus negative 1 is 1. And now we multiply again the 0 times our number. Negative 1 times 1 is negative 1. And we add these. Negative 5 plus negative 1 is a negative 6. And now negative 1 times negative 6 is a positive 6. I add these together and I get 0. This is your remainder. This is your quotient. And I told you that the degree is always 1 fewer, so since we started with x cubed, I know that this is the coefficient for 1 fewer, which will be x squared. This is the coefficient for the next one down. And this is the coefficient for the next one down, which turns out to be my constant. So x squared plus x minus 6, and that's the exact thing we got up here, only way faster. So the process is the same. Bring down the leading coefficient, multiply your 0 by that number, and write it down. Then you add down, multiply the 0 by that number, and write it down. Add down. Multiply the 0 by that number, write it down, and add down. If your remainder is 0, then this is a 0, and you've got your quotient. So we'll do the same thing over here. We've got, now you have to make sure all the exponents are there. So 3, 2, 1, 0 are the exponents. So now I can just bring down their coefficients. Write in the 0, which in this case is 3. Bring down the leading term. 3 times 1 is 3, plus 2 is 5, times 3 is 15, plus negative 5 is 10, times 3 is 30, plus negative 6 is 24. There's my remainder, just like we had before. These are the coefficients to the quotient. So 1x squared plus 5x plus 10, and that matches the quotient we got before. Synthetic division is clearly way faster than the long division. We now know what f of 3 is because we divided by 3, so we know what f of 3 is, and we've got this quotient. So that's a nice, quick way to do it. And notice the process is always the same. Add down, multiply by the divisor, write it down. Add, multiply that by the divisor, and write it down. Add, multiply that sum by the divisor, and write it down. And then add, and so on. And we can do that for any polynomial to find if a particular number is one of the zeros. So that is how we'll do synthetic division. And remember, the remainder equals f of what you're dividing by. So if I needed to quickly find f of 4, I could just divide by 4 and see what I get. Now 4 will not be a factor of this, and later when we talk about the rational zeros theorem, you'll see that that can't be. But 1, 2, 3, and 6, the positive or negative versions could be. And we found that negative 1 is. Let's do some more. A little more practice in here. So I want to find a good problem here. They give us f of x is x to the 4th minus 26x squared plus 25. Is 5 a 0? Well, I could plug 5 in, f of 5. So that's 5 to the 4th minus 26 times 5 squared plus 25. So let's see, 5 to the 4th is 25 times 25, and that sounds like 625 if I remember right. This will be 25 times 26, so I believe that's 650. Yeah. Plus 25, so I get 50 minus 650, that's 0. So f of 5 is 0, so the answer is yes. Not too bad. Or I could use synthetic division. So notice I'm missing an x cubed. So I would have 0x cubed. I need to account for that. I'm also missing an x. So I need to account for that. So bring down my coefficients. I've got 1x4 to the fourth plus 0x cubed minus 26x squared plus 0x plus 25. And I'm going to divide this by 5. So watch how fast this can be. Bring down the 1 times 5 is 5 plus 0 is 5 times 5 is 25 plus negative 26 is negative 1 times 5 is negative 5 plus 0 is negative 5 times 5 is negative 25 plus 25 is 0. I ended up with a 0, so the answer is yes. It is a 0. They're probably both equally fast because this is really, our function is really only a trinomial. So plugging in a value doesn't take too long. Synthetic division doesn't take too long. What are the benefits? Why would I do synthetic division instead of just plugging it in? Plugging it in gives me that answer. What if they added this question? What are the other zeros? I can sit here and pick numbers all day long and plug them into the formula and see what I get. And every one that gives me a 0 is a 0. But one of the benefits of synthetic division is now I can take this quotient and plug values into that one and see what I get. So if I were to say divide this quotient, oh, I don't know what another one is. We could try positive 5. It's nice. Oh, I'm not sure this is going to work. 10 times 5 is 50 minus 1. Yeah, that one's not going to work. So 5 doesn't work. It was just taking me to the wrong, a bad number there. Maybe a 1 would work, or a negative 1. So if I bring down the 1 times 1 is 1, add those together, 6 times 1 is 6, plus negative 1 is 5, times 1 is 5, plus negative 5 is 0. And I just found another 0. And now I've got a quadratic. X squared plus 6x plus 5. And I can factor that bad boy, which I believe is the technical term. Just like that. And x equals negative 1, x equals negative 5. I have the other zeros. I've got all 4 zeros. And I can't get that by just plugging a number in. And so we are at the end of time, but I wanted to show you that there's great value in using synthetic division if you have any questions like this one beyond, is that number a 0? If you do, synthetic division will get you there faster than guessing and plugging them into the formula and seeing what you get. Because notice each time I did division, this would be an x cubed, this was an x squared. I decreased the degree, and once I got down to a quadratic, I could just plug it into the quadratic formula, or in this case, just factor it. So I really want you to learn synthetic division. It's going to make a difference when later on when we need to find all the zeros. Do you have any questions before we call it a day? I feel like it kind of went fast, but it seems like every day does. This is recorded, so you can go back and look at it again if you need to. But it sounds like we don't have questions. If you have some over while you're working on the homework, send me an email or bring the question with you tomorrow, and we will look at them. But other than that, let's call it a day, and I'll see you tomorrow. You're welcome. Have a good day.